Thank you very much. Thank you for the opportunity to talk to such a large group. My name is Oner and I am with InCirT. This will be a general overview about the FirstTo6G project. So first of all, let me give you an abstract. What is our focus? We are focusing on a new type of data converter based transceivers, receivers, and transmitters for the upcoming 6G communication. The main objective here is that we want to realize or enable the realization of the 6G by improving the radio hardware, where we're seeing a lack of technology in the research today. The whole project is at its heart based on this new concept of implementing DACs and ADCs that can be wideband and at the same time also high quality, such that you can use efficient modulation types. Also for the front ends, we will have highly advanced RF front-end technologies designed directly for 6G in different bands, as we will talk soon. Some of the key goals and strategies that we have here is, as I mentioned before, we want high bandwidth efficiency and high power efficiency. We want form factor and cost to be small and effective because we see that 6G can only be widespread technology if the necessity, form factor, and cost KPIs are met. In the same time, we want to show that we can do technology integration with a lot of partners, to which I will talk soon. Some facts: the duration of the project will be 42 months. It's a little bit longer because it involves hardware production, such as IC production. The budget is approximately 5.4 million euros, and the consortium, we have 6 partners coming from 5 countries. And this is a photo from our first kickoff meeting, just to not have only facts, but also some faces behind the partners. Let me talk more detailed about the partners. We have a combination of academic partners and SMEs. On the SME side, we have Sivers Semiconductors based in Sweden with extensive experience in RFIC and front-end design. Then we have Argo Semi, is also an SME based in Greece. They have a very strong background in microelectronic engineering, and their role in this project will be developing parts of the wideband front ends in combination together with Sivers. And then we have InCirT, the company I'm with. We are a startup SME from Germany, and we are in the same time coordinating the project as well as delivering the high-performance data converters. On the academic side, we have RWTH Aachen University based in Germany and the Yeditepe University based in Turkey, who both of them will be working on the RF front-end side for very high frequencies. And we have, last but not least, Shiprom. It's a project management company based in Switzerland, and a role in this project is to do the management, dissemination within the project here. Let me give you a little bit of a background why we come up with the ideas leading to this proposal. So what we see in the market is that there is a rapid growth in data usage. If we think about the mobile phone usage, it goes from 12 gigabit per month and it grows annually by 20%, which means there will be a lot of need for very high data rates. And actually 6G is targeting actually that to deliver these high speeds and these high capacities. And what we have to have is we have to enhance the data rates, and we have to use therefore wide bandwidth spectrum. There is one option that we just heard to, which is using the sub 15 gigahertz bands. But on top of that, there are also other frequency candidates that are very highly like usable candidates for the 6G communication. And if you look into the latest release of the 3GPP, we see that in the D band, there are candidates that can be used for the 6G communication. In the same time, we have to think about D band communication will not be covering, delivering a very good coverage, and therefore we have to think about 6G as at peak performance, working in the D band, operating at the highest possible bandwidth, but in the same time also being able to cover lower frequency bands, such as the 60 gigahertz ISM band, this below 15 gigahertz bands, as we just heard in the previous presentation. And in that regard, we have decided to phase or to outline the project into parallel branches, One is that we would like to have a complete transceiver solution operating in the 6 GHz ISM band, and the other one will be a solution for the D band in around 140 GHz. So as I mentioned, there will be two solutions being implemented within the FirstTo6G project here. One is for the D band, the other one is for the V band, and we have here specific hardware innovations that are required. We have to have modulation bandwidth as high as 8 gigahertz and even 13 and more gigahertz instantaneous as a single band to be covered, which is a huge problem considering the DAC and ADC requirements. In the same time, we have to be energy efficient, we have to be compact in form factor, it has to be cost efficient, but it also has to deliver trustful communication. And the ambition of FirstTo6G is to exactly develop these data converters alongside with their RF front-end technologies. And with that, actually, we are addressing the current technology limitations in signal quality and the power usage. And yeah, in total, what we do here is we collaborate with partners from different areas in order to get these goals. As I mentioned below, in the V band, in the below 100 gigahertz solution, what we are trying to do there is, to implement there is, from InCirT side, we will deal with services coming from an FPGA for the baseband processing. We have the DSP and FD DACs, FD ADCs implemented on a 22 nanometer FDSOI technology, as well as the front end components coming from Argosemi and Sierra Semiconductors will be implemented on this same technology. And we are targeting to be able to cover a total of 8 gigahertz of coherent modulation bandwidth with speeds of up to 56 gigabits per second and even more. This is what we're targeting in the below 100 gigahertz solution. So then there is actually the D-band solution, which is a combination of the data converters that we develop at InCirT with some very sophisticated and very high frequency RF components, front-end components operating in the D-band. And the decision here was to see if we can do it actually the complete system in a global 22 nanometer technology, but actually in the end we figured out that it would be the best solution in terms of performance to have a two technology solution such that RWTH Aachen University and the Yeditepe University from Istanbul, they will be focusing their work for the front end to be in a CG technology in order to implement the up conversion blocks, the phase shifters, the combiners, but also the power amplifiers and LNAs. So let me give you a couple of specs that we are targeting here. And when we talk here about the two solutions, the V band and the D band, as you can see, if we look at the modulation bandwidth, the one is up to 8 gigahertz of modulation bandwidth. In the D band, what we are targeting is up to 16 gigahertz of modulation bandwidth. As you can see here, it's double the speed. It is because when we go back, what we will do here is basically, we have already these super high modulation bandwidth DACs and resolution ADCs. And the target here is, compared to the V-band solution and the D-band solution, to implement it twice, and on top of the existing FD-DAC architecture to implement a frequency interleaving, and in that way to extend the bandwidth to be the double of the 8 gigahertz, which is then here 16. Yeah, there are a couple of other parameters given here with the total energy consumption, which I also think is very important here. For the single chip solution in the 60 gigahertz frequency range V band, we are targeting a total power consumption of less than 1.5 watts, including the DSP, including the front ends, but of course excluding the power amplifier in this case. For the D-band solution, the same applies here with the 2.5 watts, which is the speed. This is the power consumption that we have calculated in our first estimations for the complete power consumption of the multi-chip solution. So how did we organize the work packages? On the right-hand side, you can see the general organization of the work packages. And if I would like to comment on those, we have, first of all, the work package 1, which is the system modeling. Main contributor here is Argosemi. The system modeling is basically the whole architecture, and it creates a baseline for the complete work that's coming afterwards. And that's also why, since we have kicked off the project, we are highly focused and working on defining the interfaces between the partners, defining the interfaces between the hardware modules, and with that, we are actually getting through. And based on that, we will do the development of the data converters in the work package 2, which is feeding into both directions, the above and below 100 gigahertz front-end components. And in all together, we will in the end have a demo and assessment. And of course, we will also work on dissemination and exploitation. And of course, there is a work package 7, which is the management part. It's overarching the coordination of all the work packages and ensures alignment and project cohesion. So let me also give you a couple of...
Please wrap up because your time has expired.
Okay. Okay, thank you. Then the anticipated outcome is basically the implementation of all the things that I've just mentioned before. Thank you very much.